So strain first it comes with strain and then it comes the stress. One more thing, I mean when you apply any force, what does that force do?
Abolish deformation.
When you apply force, what it will do?
It will pressure the area.
It will try to deform it. Any force. If it is a spring, if it is a rubber, if it is a beam. So if you, for example, you have a beam and you apply a force on the beam, so what does happen? It will try to deflect. So once it will try to deflect, the internal resistance of the beam will come into action. Which is the internal thing. For example, if you slap someone, so the internal feelings what you get are the resistive one. So then you slap it back. So this is the same thing. Once you apply any force on a beam, so beam get internal resistance, and that internal resistance causes internal forces. There are three types of internal forces: normal force, shear force, and bending moment. There is torsion, but that is out of the subject, and I hope that maybe when you study like the more advanced courses like advanced structure analysis and finite element analysis, or in your graduate program when you do your master and your PhD, you will study the torsion design. But for the most of the cases, we don't have to deal with the torsion. Torsion is the biggest problem, especially when the loads are acting at what should I say? Not symmetric. When the loads are acting at some eccentricity. You know eccentricity? Okay, hold on. Eccentricity, for example, if the load is not acting at the center, this is your beam and the load is acting at the center, but if the load is acting on the side, on one side, so it will try to twist it. So there is eccentricity. What is eccentricity? It is a distance from the center line that is known as eccentricity. Okay, let's talk about, we are not going to study torsion at all. If you are interested, you can come in my office, I can teach you. But it's not maybe in your whole course, in your whole undergraduate program. It's highly unfortunate for some of the students, but this is your course. Even when I was a student, I didn't study at undergraduate level. I studied torsion at graduate level because there are a lot of theories and advanced mathematics which are involved in torsion. But we design for the torsion. We can design for the torsion. Now the computer softwares, let me tell you about the design and the real structural analysis. I will teach you SEP because I want to show you the real structural analysis. I mean, as an engineer, I don't remember that in any company when I have done a manual analysis of any structure, or I have drawn a shear force and bending moment diagram of a bigger frame or a very complex frame. But yeah, for the small beams you can do it, but I didn't do it for my professional career when I did job in different companies. But I use the computer programs, and everyone use those computer programs. Like the calculators, no one is now doing the multiplication, but they are using the calculators. The same thing is happening in the companies. But if you have a poor background knowledge of structural analysis, you can do blunders. What's the difference between you, engineer, and a computer operator? For example, I can teach that software to any guy who is maybe like a high school student, and he can operate much better than you. But what about the background knowledge? That is the most important thing. So this is the time in which we will solve one problem and we will compare the manual analysis with the computer aided analysis. And I think you will not get this opportunity for the rest of your life. I'm sure about it. Until and unless you do your personal effort. You get what I'm saying?
Yes.
That we will do some problem maybe after this chapter here, and we will also do the same problem in the computer. I think the students before, like when I teach this program or when I teach this course, I teach in parallel SAP, Structural Analysis Program. There is one of the most famous computer programs used for the structural analysis. SAP, STAT, these are the two programs. ETABS, yes, but ETABS is very specialized program for the buildings. That is not for the structures. Because ETABS is like an extended three-dimensional analysis of building systems, ETABS. But SAP is Structural Analysis Program. I will give you the option, but if you know how to operate SAP, you can operate ETABS. Okay? And you know, there is a very small gap between analysis and design. In computer-aided analysis, the most difficult thing is analysis. The design is what? Just press one button. Give the code, give the properties, and give the dimension, and then press one button, it will design. Do you understand? The most difficult thing is analysis. Okay?
From where we can get the program?
For me. As you are getting your book chapters.
How many get?
How many mega you should say? Actually the new program may be in giga, but I have the older version and you don't need the advanced version. You need the basic version, and it would be 500 to 700 MBs. Okay? It's already in my, I will share the link with you and you can download. I think you had 2015? 13? Yeah. Engineer Amar Al-Jabbar, his senior design was with me, and I remember they did the analysis of a multi-story building on ETABS or SAP?
No, ETABS.
ETABS. Yeah. So they visited some offices, maybe in Riyadh and one in Dammam. Yeah, and they collected some information, some real models of the building, drawings, and the information, the material properties, the loading, and then they modeled the same building in their senior design. But that was not only their senior design. Then we did the seismic analysis. We changed the seismic forces. I remember.
Yes, the different seismic forces.
Different seismic forces, different frame. Like we changed the location of shear walls. That what is the effect of the shear walls on the building geometry, or if you change the building geometry, then how this response, the displacement will change. So it's very interesting. It's a good thing, and he can tell you that the people in the offices, in the design offices, they are using either SAP or ETABS. Is it true?
Yes.
Okay. So let's talk about the internal loadings. So in the end of this chapter, we will do one problem in the computer. Okay? So first of all, how these internal loadings develop. For example, if you have any structure, you can see the members. The members are connected and the forces are transferred from one member to the other member. So what is the purpose of a structure?
To connect the load to the ground.
What is the purpose of beam? To safely transfer the load from slab to the column. And what is the purpose of column?
To transfer the load, yeah.
From
the
foundation.
From
Beam to the foundation.
To foundation.
And what is the purpose of foundation?
To transfer the load to the ground.
To the ground, safely. That's
Safely.
the most important thing.
Yes.
Safety. Okay? So if you apply any force on any member, I told you, the member will not remain silent. It will produce internal forces. And when there will be a problem, when the applied force will be greater than the internal resistance, what will happen that time?
It will
Yeah.
then
It
fail.
will fail.
Yeah.
It will collapse or it will break. It depends upon the material. For example, if it is steel, it may deform, but if it is concrete, it may crush. If it is plastic, it will break. So it depends upon the material, what material you are using. Internal loading, let me tell you, many of the students, they remain confused till the end of their graduate program. What is positive shear? What is negative shear? What is positive moment and what is negative moment? Is it true? How many of you remember all these things? I think you have studied in statics and then strength material. This is the third time you are going to study. I hope you will be the expert of all these things after this chapter. Even you can do the better analysis than me. Okay? I expect it from you. Well, I tell you in a short way, any axial force, there are three types of effects. For example, there is a beam. You apply a force on this beam and it has two reactions. If I say this force is P, this will be P by 2, this will be P by 2. You want to apply any axial force or no? In this case. Okay, we will discuss axial force later on. Okay, so you cut a section. Okay, if there is any axial force, let's also apply an axial force which is acting in this way. So you cut this section. So I cut this section. For example, now I draw this section. This is E by 2, this is, I say M. Okay, that's all. Is this section in equilibrium?
No.
How many of you say yes? Is this body is in equilibrium? No. How I can bring this in equilibrium?
There must be a force to the right and downwards.
Yes, there should be a force down. I call this force as V. V. And there should be one force acting N. Is it in equilibrium? Can you start your attendance from here? Now, is it in equilibrium?
Yes.
The moment.
Is it in equilibrium?
That's right.
How many of you say yes? Please raise your hand. No, it's not in equilibrium.
Moment.
It is rotating in this direction. See, it is rotating in this direction. Is there anything which is balancing this rotation?
No.
Moment.
No. So you should have a moment. So there will be a moment which will try to balance. Okay, how much will be this V?
Equal and
P over 2.
Yes, for equilibrium it should be equal to P over 2. And how much is this N? It should be equal to N. And how much should be the moment?
B over 2 for the distance.
Yeah.
If
P
this
over 2
distance
is
is X,
P for 2
in the distance.
G into P over 2.
P over 2x.
Yes. So, and what are these forces? From where these forces are coming? These forces are coming inside the beam. So that is why we call all these forces as internal loading. If you see now these two diagrams, this one and this one, I think you can understand. Please have a look. I give you 1 minute. Have a look on these two diagrams. Then I will tell you what is positive and what is negative.
The right section.
Forget for that. Give me some time. First, just have a look on these two diagrams. I will explain you what is right and what is left. It is the same concept. Okay, if you want to take a section from right, just cut it from here and do the same thing, you will get this diagram. Have a look on this. So if you see, now you can have a question why it is an upward force.
Should be opposite the.
It depends upon
on the
the
force.
value of this force and this reaction. If this force is 10 kilonewton and this force is 5,
This 5.
It should be 5 upwards.
so it should be 5 upward. Do you understand? So it depends upon this value. How much is this force? Okay? This force. Okay. So then you can determine the reaction in which direction you have to put the moment. I think you understand that how these forces are coming. Now, positive and negative.
We can assume it and when we calculate.
Don't need to assume. I tell you. Now, okay, I keep it here. First of all, axial force. Positive axial force, it produces tension or elongation. Any force, any axial force, in this case the axial force is N. Any axial force which tries to elongate the beam, it is positive. Okay? Any normal force is axial force which tries to elongate the beam is known as positive. And any force, for example, if you apply a force this way, so it will be negative. Number 2, shear force. Positive. I mean, I'm just telling you the positive. The negative will be the opposite. Okay? Positive shear. If you see this shear force is trying to rotate this with the help of this reaction in the clockwise direction. Can you see?
Yeah.
Any shear force which tries to rotate in the clockwise direction is positive. Rotation in clockwise, positive. For example, if you see this shear force is also trying to produce the clockwise rotation. I'm talking about the shear force. And now the moment. Any moment. Sorry? Not counterclockwise.
No, it should be like this.
This is the moment, any moment. For example, if you apply a force on this beam, then there will be a moment, so this beam will try to bend this way. For example, if you have a moment here, so how this moment will try to bend this beam? This moment will try to bend this segment like this. Conjugated up. Concave up. So positive moment concave up bending. It is the most simple way to understand that which force is positive and which force will be negative. The moment and the shear. If any force the axial force produces elongation, it is positive. Shear force, if a shear force produce a clockwise rotation like this, downward shear here, downward force, positive. Positive moment, any moment which tries to concave up is positive. Okay? Now I show you the more diagrams so that it will become more clear to you. I'm going to erase this. It's a very difficult job. That's why I don't use a thick marker. All of these markers are, having the ink remover, but I don't know why.
That's the quality itself.
It's
The quality of the work.
Low quality.
very, very low quality.
The smallest board in the whole university.
Maybe.
With engineering.
Not good
No.
at engineering.
Green apple.
So you must be surprised that why I don't use the thick marker. That's the reason. That's why I like this one. Okay. Okay, let's go next. So, this normal force will be positive or negative?
Positive.
Positive. This shear force, clockwise, positive or negative?
Positive.
This moment,
Positive.
now tell me. Now you can see the sections, left or right. So, if you cut a section from right, still, any moment which tries to produce the concave up, it will be positive, and any moment which tries to put the deflection in the concave down way, it will be
Negative.
negative. Let's do one small example. Can you see this house? If it's not clear, I can make it more clear. Yes. So if you see, there are small girders, or you can call them joists. The roofing is resting over the joist, and joists are resting on a big beam. Can you see?
Yes.
Yes.
So the slab load is coming first on the joist, and those joists are supported by a big beam. So the slab load on the joist, it will be UDL or point load. The load of slab on the joist, it will be UDL, uniformly distributed load, or a point load.
Uniform.
Point.
Uriel.
UDL, point.
Point.
In distance. Not point.
So that it
See here,
Because each one rotates.
if I see each joist, for example, the half of this slab, and half of this slab is resting on one joist like this. So the load on this joist is UDL or point load.
Uriel.
It is UDL, uniformly distributed load. And how much is this load? How you can find that?
Unit weight into the area.
The load per unit area multiplied by
The thickness and the
This distance.
The width.
the distance of the joist multiplied by the load per unit area. This is the problem. The building roof shown in the photo has a weight of 1.8 kilonewton per square meter and is supported on 8 meter long simply supported beams. So the roof load is how much? 1.8 kilonewton per square meter, and these are 8 meter long beams. And beams are spaced 1 meter apart. Each beam shown in the figure transmits its loading to the two girders located at the front and back of the building. Determine the internal shear and moment in the front girder at point C. Okay, where is the point C? Point C is somewhere here. I will tell you, I will show you. This is the point C. And this diagram is a free body diagram of that whole structure. First, let's talk about the joist. These joists are running perpendicular. Okay, 8 kilonewton per square meter, 1.8 kilonewton per meter square is a roof load. It's already multiplied by the thickness.
The whole thing. The whole roof.
And this is 8 meter span.
Okay.
I'm going to show like this.
So we have 8 beams.
This is 8 meter simply spotted. How much is the load on the roof per length? It will be UDL, but how much will be that?
1.8 into 8.
1.8.
1 meter is the spacing between the girders, between the beams.
1 meter.
So it will be 1.8 kilonewton per meter. How much will be this reaction?
Multiplied with
No.
This is
Multiply the
8.
distance. Multiply by 4.
7.2.
By 4. 1.8 into 4.
How much?
7.2.
7.2 kilonewton. So where this load will go?
To the columns.
No.
The beam.
To the bigger beam. This is the load on the joist. The roof load on the joist, and here is the reaction. This reaction is going to the bigger beam.
Oh, okay.
Here we have bigger beam. Try to understand the structure. This is what is your job. So if you see this diagram, now you can see. This reaction, all these forces are 7.2 kilonewton. Why this is 3.6?
Because it has half the area.
Is it right? How many of you do not understand why it is 3.6?
Because this half from right and half from
It's exterior. Because there is no slab or no load on the right. It's only 0.5 multiplied by 1.8. You will get here 3.6 and 3.6. Okay?
again.
Because the load on this beam is only half of this part, it will be 0.